Welcome back to episode 2. This time we get out in the depths of the universe to ask that fundamental question, how big is space? And to answer it, we're going to utilize technology. Things like the Hubble Space Telescope, the Mount Wilson Observatory, huge observatories around the world to look out in the depths of the universe, measure distance, find out clues to answer our question, how big is space? Hi everyone, and welcome back. When we peer through the sphere of stars that we see in a nighttime sky, we enter cosmological space and into the realms of galaxies. Galaxies are the largest structures we find in the universe. Galaxies like our Milky Way, for example, where we live, inside of which is gathered everything you will ever see, touch and feel. Things like our sun, things like planets, and even our moon, and everything else gathered inside of our Milky Way galaxy. But beyond that, there are many more galaxies, like this one, for example, which is the Andromeda Galaxy, our closest neighbour in the universe, some 2.3 million light years away. And this amazingly beautiful galaxy called Messier 51, or the Whirlpool Galaxy, some 26 million light years away. How can we see galaxies that are so far away with such stunning resolution? This is because these objects are enormous. It might take 100,000 years travelling at the speed of light to traverse across a galaxy like our Milky Way, for example. Could you imagine 100,000 years? Every second of those 100,000 years you travel at 186,000 miles in every single second for 100,000 years to get across our Milky Way galaxy. So clearly, space is very, very big. But to answer the real questions, we need to leave behind our Milky Way galaxy and get out into the depths of the universe, where there are many, many more galaxies, and where our question will finally be answered. In March 1929, Edwin Hubble published a paper that would quite literally revolutionize the way we looked at the universe. Before this, the general consensus on the arrangement of our Milky Way and the universe at greater distance was really quite a simplistic one. The majority of people believed and thought that physically, spiral nebulae like the Andromeda Galaxy existed on the periphery of our Milky Way galaxy. It wasn't until Edwin Hubble's landmark observations using the 100-inch telescope at the Mount Wilson Observatory in Pasadena, California, that Edwin Hubble was able to perfect a system to measure distances to galaxies. Edwin Hubble's initial estimation to the distance of the Andromeda Galaxy was 900,000 light years, putting it way beyond our Milky Way galaxy. So in the mid-1920s, clearly the universe grew exponentially bigger. Edwin Hubble went on to look at 48 more galaxies and measured the distances using his newly found technique. Hubble looked for a very special type of star known as a Cepheid variable star, the fundamental basic principle being quite simple. If you know how bright an object is, you could measure its distance. But what Edwin Hubble found wasn't expected at all. The general consensus then was really quite a simple one. Our universe was infinite in age and size. That meant that when Edwin Hubble went searching for galaxies, he could have expected galaxies to be moving in all random directions. The discovery that Edwin Hubble made by looking at the light that these galaxies emitted was that the light waves were stretching out, meaning there was a cosmological Doppler effect happening. What that essentially means is that as the galaxy that Edwin Hubble was looking at and our planet Earth from where the telescope was based, the distance between these two objects was increasing. When that happens, the light that was being emitted from this galaxy was stretching out as it traveled these extreme distances through space towards the telescope. This stretching increased the wavelength of the light and decreased its frequency. This alters the color of light, meaning light from these distant galaxies became redshifted, moving to the red part of the spectrum. This is exactly what you could expect to find in a universe that was expanding. Imagine you being at a central point in the universe, an arbitrary position. You can invent it for yourself. And when you look out in all directions of the universe and you measure distances to galaxies, just like Edwin Hubble did, what you would find is over 95% of the galaxies you would observe would display this redshift, meaning the distances in between you and these galaxies is increasing every second that passes. So if you extrapolate that information out further, then what you could absolutely expect to happen is that if you were to put time in reverse, let's say, and let clocks tick back, how long would those clocks have to tick for until everything you can see, touch and feel in the universe, the galaxies at extreme distances, everything, occupied the same position? Upon further inspection of Hubble's data, what he also realized was that the rate at which these galaxies were receding away from us was proportional to their distance, meaning the more distant a galaxy is, the faster it was moving away from us. This is precisely what you would expect to find in a more or less uniformly expanding universe, that galaxies at extreme distances would move away from us faster. This is, of course, what we call nowadays the Hubble law and the Hubble flow. Edwin Hubble undoubtedly made one of the most important contributions to modern cosmology. But little did he know that in 1990, a telescope would be launched into space, named in his honor, that would make a contribution that not even Hubble could have seen coming. Because that telescope that we now know today to be the Hubble Space Telescope stared at a tiny patch of the sky and gave us deepest, fundamentally important view that science had ever seen of our universe. Go outside at night and on the end of your finger, place a grain of salt. And carefully, on a preferably non-windy night, extend your arm out so it's at arm's length and hold it up against the sky. Because that grain of salt will obscure an area of the sky equal to the field of view of the picture that you can see behind me now. That one grain of salt obscures 1 square millimeter of the entire sky. And in that image, Hubble captured over 10,000 galaxies. When we look at the Hubble Ultra Deep Field image, it's pretty difficult if you're not a research scientist or an astronomer to make a lot of sense of it. It's like any other image we'll ever see of space almost, with a black background, a two-dimensional field and lots of interesting objects to look at. But when we truly start to understand the magnificence and the importance of an image like this, only then does it truly come alive. The first thing I want you to try to do is imagine that this has 3 dimensions. Well, as you can see now, the galaxies are starting to move. So what I want you to imagine is that every single dot, dash and scratch you can see on this picture now is a galaxy like our Milky Way. Some are bigger, some are smaller. But in essence, they're all galaxies, and each one of them could contain upwards of 100 billion stars. Every dot, dash and scratch, it could be a Milky Way galaxy. And remember, all it is 1/30 millionth of the sky that you're looking at. Now, what you can see is that the galaxies in the foreground are now starting to move through the field. This is because these galaxies are closer to us when the image was taken. So what we're essentially doing is, as we move through this field of galaxies, time ticks backwards. So we're going through the evolutionary history in cosmological time, but we're going backwards instead of forwards. And what you will start to see is some galaxies start to change. And as we move back in time, we see galaxies that are relatively familiar to us, like this galaxy, for example, over 7 billion light years look back time. This is a very distant galaxy, and as you can see, it has spiral structure, it has shape, and it has a form to it. But as we move through the field of view and as time runs backwards, we run out of galaxies. Now no longer can we see these well-formed adult grand spiral galaxies. Now we see small irregular shaped galaxies. Why? Well, because when you're looking at the universe now on this image, we're seeing the universe as it was at very, very early times. Nature hasn't long enough to make these galaxies into the structures we see today. So we see them like infant galaxies, snapshots almost of what the universe looked like 10, 11 billion years ago. That's what these galaxies looked like then. And then as the movie continues and we move through the field of view of these galaxies, we don't see anything at all. We get to a point in the evolutionary history of the universe when there isn't any galaxies at all to see. Okay, well, this is clearly starting to get a little bit more interesting. What does it mean to say that the only boundary in the universe so far is time? Well, to answer that question, we need to go all the way back to the very beginning of the universe itself. Most scientists are united in believing that the age of the universe to be some 13.82 billion years, meaning clocks have ticked for that amount of time. And the very first second a clock ticked was at the point of the Big Bang, and they've ticked ever since then. And when you add all those seconds together, you get 13.82 billion years worth of seconds. This is the estimated age to the universe, and it's a good estimation. So what that means for our quest in establishing how big is space, it means that light has had 13.82 billion years at which it can travel at the speed of light. And because the speed of light is of a finite speed, it has a speed limit. This means that we can see back to the very, very earliest times in the universe, because it takes time for light to travel across the sky. Even on a beautiful clear night, if you look at the moon, it takes just over a second for the light from the moon to reach your eye. That means you see the moon as it was 1 second ago. If you extrapolate that out a little further, we look at the sun in the sky. The light from the sun takes just over 8 minutes to reach our eyes. So we see the sunlight as it was 8 minutes in the past, all due to the fact that light does not travel at an infinite speed. It has a speed limit. What a payoff! Because what that means, nature has given science the tools by which we can explore the universe. So it appears that time is our first boundary, and it will be pretty much our only one. But our universe is strange. It is awe-inspiring and weirder than we could ever imagine. And by exploring the very boundaries, the margins of our universe, we find objects to examine. And one of those objects is what I want to introduce you to next. And it has to be the most awe-inspiring, spine-tingling discovery. So sit back and relax while I explain to you Galaxy GNZ 11 and its implications. After the amazing success of the Hubble Ultra Deep Field, scientists were planning to probe even deeper into the observable universe, and a plan was put together to form an observing program known as the GOODS program. This was the Great Observatory's Origins Deep Survey, a survey that would unite digital information from a host of space-based telescopes, as well as telescopes here on the Earth's surface. The GOODS survey was an attempt by scientists to look as far back as was possible to probe the early formation of galaxies. But one galaxy in particular stood out amongst all the rest, because this galaxy was the most distant galaxy ever observed. It's known with the very catchy moniker GNZ11. The Z11 is a reference to its redshift, its spectroscopic redshift, that was researched by scientists using the GOODS survey. The idea behind this designation of Z11, this redshift number, this gave it a distance that was measurable. And that measurable distance was 13.4 billion years of look-back time. This isn't a true distance, however. It's quite often mistakenly talked about in popular media and on YouTube channels that galaxies like GNZ11 exist at a distance of 13.4 billion light years away. This is incorrect. Galaxies like GNZ11 are so distant that the light from those galaxies has been travelling towards us for 13.4 billion years, but this is not the distance to the galaxy. Because in that intervening period of time, of 13.4 billion years, the expansion of the universe has pushed this galaxy ever further and further away from us. So its proper distance, when you take into account the effects of dark energy or this vacuum energy that is probably responsible for the expanding universe, when we allow for that, its proper distance is some 32 billion light years away. Well, we need to look a little bit further at GNZ11 to understand what's actually happened and what's going on. In this image, we zoom through the field of stars in the constellation of Ursa Major, honing in this good survey to find galaxy GNZ11, this tiny little dot of light that you can see on your screen now. Now it resembles Mr. Blobby. It's pink, for example, and has not a regular shape at all. It doesn't look anything like our Milky Way galaxy, for example. Well, it wouldn't, because it's about 1% of the mass of our Milky Way galaxy. It's going through a rate of rapid star formation. The galaxy should appear blue, because it's full of these big blue stars. But because the light has stretched out and passed through this cosmos over the last 13.5 billion years, the light has been scattered into the infrared. And this is why probing the universe in the near infrared and the far infrared is so important for research astronomers to try to find these most distant and early time galaxies that give us a better insight into how our universe has evolved. So why is galaxy GNZ11 so important? Well, it's fair to say that because the light from this galaxy left around about 400 million years after the Big Bang and has been travelling towards us ever since. So think about that. That light from this galaxy has been travelling through the universe at the speed of light for 13.4 billion years. And then it shows up on the goods data. So what it means, as far as we're concerned and how big is space, is this. What I want you to imagine is standing in a darkened room and somebody turns on a light bulb. Just as sure as the light from our imaginary light bulb travels in all directions simultaneously, so does the light from galaxy GNZ11. If that light has travelled towards us for 13.4 billion years, marking the boundary to our observable universe, then surely the light from this galaxy has done exactly the same in the opposite direction, into a part of the universe we can never see into. Why? Because there's never been enough time for light from these most distant reaches of the universe to travel towards us. So we can't see into that part of the universe. But this is evidence to the fact that we cannot be at the center of the universe. We cannot occupy some special point. And this boundary in the universe of time is the real boundary we'll always come across. But what it also shows us is that when you're on the very extremities of our universe from where we are now, then light has travelled throughout the rest of the universe that we can never see into, telling us that beyond our observable universe, there are many, many more billions of galaxies that we will never, ever be able to see. Because of images like the Hubble Ultra Deep Field and because of research programs like the GOODS program, astronomers and researchers have been able to estimate and calculate the amount of galaxies that exist inside of our observable universe. And the modern value tends to be around about 2 trillion. So 2 trillion galaxies like our Milky Way exist in that sphere of light we call our observable universe, which is just the part of the universe where time has allowed light to travel towards us. But we've just demonstrated with our thought experiment that if you could place yourself on the very boundaries of the universe where GNZ11 is, then you would see into a universe that we can't from our vantage point. So we see already there are 2 components. We have on one hand our observable universe, and on the other hand we have the complete universe, into which we can never ever see into. It has been said that comparing them both is like comparing what our observable universe is to the complete universe, is like comparing what an atom is to our observable universe. If analogies like this are true, then the universe will be way bigger than we ever imagined. But what lies beyond the extremities of it will always be governed by time. So I hope you found out in our little journey through the exercise of trying to understand how big is space, is that we'll never really probably be able to fully understand the enormity of our universe. But there are constraints laid upon us by time. And by understanding the natural laws of nature and understanding time, we have all the equipment we need, seemingly, to go out and answer all of these questions. In the next section, I'm going to explore the Big Bang and the extremities of high energy physics at both ends of the existence of time and at the universe's inception itself, and how it will all end, and how we, through research, we can better understand the shape of the universe, the age of the universe, and ultimately its fate. So I look forward to seeing you at the next production of How Big is Space?